Okay, hi everybody. Here's your video from home. Sorry for the sound quality already. I didn't bring my ShamWow goggles. Oh, geez, it's early in the morning. Headphones. And I figured I'd just, I think one of the 2 hours I didn't quite get all of these graphs. But just take a look at them. This one for sure is 1 right and 3 down comparative to the y equals 2 to the x graph, which has 0, 1 as a coordinate. So if I take the 0, 1 and move it, I think I said 1 right again early in the morning. I meant 1 left if I said that. And then 1, 2, 3 down. Really track where that 0, 1 coordinate ends up. And then also be aware of where the asymptote ends up. So that you can look at these domain questions and range questions efficiently. This one's a range of -3 to infinity because of the border, not including -3. And then the limit, you'll be able to answer these limit questions, which I'm sure are not a problem. This one, the 0, 1, you should really do the right 3 first, and then the flip over the x-axis. That's what the negative does. Then down 5. Just imagine if you went, right 3, down 5, then flip. Boy, what a difference where that point is. That's why I say down and flip over the x-axis are dependent upon each other. No other better way to say it. So, you do the flips first before you do the moves. If you had a y-axis reflection and a right-left move, you reflect first, then you move right-left. You just got to solidify those rules. I've said that 2,000 times. All right, and then these I think I did finish in class. One I didn't do is this question. You really don't need to do this graphically, although you could. You could find out where, subtract 4 to the x from both sides and then analyze when does the graph end up being greater than 0, like we did in the polynomial chapter 2. Or, what's 9 to the 0? 1, good. 4 to the 0, 1. So when x equals, when x equals 0, these are equal. So that's the starting point of where you get some good answers. And then when you plug in 1 for x, that's 9. 4 to the first is 4, so 9 is greater than 4. So there's a start. It shows you that this starts getting bigger than this side. I don't know, maybe when you plug in something greater than 0. But you also have to check decimals on that too, like 0.1. What happens when you put 0.1? And that's 9 to the 1/10th power. 10th root of 9, how is that compared to the 10th root of 4? Well, that's still larger on this side. So, and then negatives, just think of -1 if I plug that in. This would be 1/9 and this would be 1/4. Now this is when this side gets smaller. So that's why x is greater than 0 is the solution for this, either graphically or just thinking about it. All right, I'm going to pop around here. I'm not going to show this next. I'm going to go to stuff that we should be able to do based off of yesterday's notes. And I should have assigned the 50 questions yesterday. So more of the same. What you got to do is trick yourself like I told you yesterday. Trick yourself that, this population model in 1990, Columbus, Ohio was 632,000, blah. And then in 2000, it's 711,000, blah. Well, trick yourself that this is year 0. So this is the initial population. Very good for anyone that actually said that. Then that makes this year 10 in the data. So that's 10 comma. So you coordinatize the question, all right? So, it says exponential, file out of your brain. A times B raised to the x for exponential real-world application questions. So instead of A sub 0, I put P or A times B to the x. P sub 0, just population at year 0 or initial population, all right? And then if you physically plug it in, this is why you end up getting the initial population being 632,000. 0 for x, 632,000 blah for y. Then Just like what I intimated at yesterday. You plug in the second data value, and I lost something. You put this 632,000. Well, I divided both sides by it. That's why it's over there. Times b raised to the 10th. Let's erase this so you don't, get too confused by this and then have it reappear. So 10, 711,000. Then you divide 632,000 from both sides, and then you 10th root both sides. There. So that's why that's all was what was said there. Now, when you 10th root, you are supposed to get a plus minus scenario going on there, but this is only, an increasing situation, so this is not when you use plus minus on this. By the way, imagine if you rounded to the 10th. This would be 1.0. If you plugged in 1.0, then there would be no growth. This would just be staying at 632,910 forever. My point being is we're obviously not going to round to the 10th. You shouldn't round to the 100th. You should almost go 4 decimal places on this because this is, real world data that, over 10 years. So you want to be as accurate as possible. So if you stopped at 1.01, you would get a much different answer than someone else that went 4 decimal places on this. And the reason I went 4 decimal places, you're going to learn this tomorrow. What is the growth rate per year? And the answer to that is this. It is 1.17% per year. This is greater than 1, so this will be an increasing situation, which it should be because you could see the data going up. All right, so that's why we go to 4 decimal places, because then you're analyzing it to the 100th percent, all right, and also for accuracy. Now, the question asks, when will it be 800,000? Well, all you have to do is solve this scenario. You plug in 800,000 here equals that, our new population model for Columbus, and then you find the intersection of those two. And there's the real specific looking graph. There's y equals 800,000. You ain't going to see that, though, if you don't get a window for y's that it's big enough. And remember, x is in years, so maybe this happens in 30 years. Let's just expand it out there and see if that's the case. And then lo and behold, you get that exponential curve that intersects right there. Find that intersection point, and I think it was, I erased it, but I think it was like, I forget. I don't know. You can do it. You're smart. Oh, I'm not supposed to say that. Sorry about that. You're very diligent in how you do your work, and therefore you have a lot of value in class. Okay. So you do the same for this. I'm not doing this one. Use the data, blah, blah, blah. Which city, Austin or Columbus, would reach a population of 1 million first? Well, guess what? If we had that, we already have Columbus's thingamajig right here. So we'd put that in Y1. We'd find Austin through the glorious math I described right here. All right, going through this process. Austin, this is 0, comma. This is 10, comma. And then in the Y3, we'd put Y3 equals 1 million. And then we'd see which curve, I don't even know what's going on. It'd be like, we're spending even way too much time on this. A little bit higher on the y-intercept, and then, I don't know what's going to happen. They may intersect somewhere. That would be the answer of when are they going to be equal. And then here's y equals 1 million. So it looks like this one would hit first. All right, so you'd pick that one because this is the year that it hits 1 million. You should be able to get that. I'm not saying which one would be right. Not that you have this for homework, but you have something else that compares the two cities. So deal with that. Okay. Okay, and then I threw these random. I found this off CUDA website. It's a nice little worksheet website, and I kept the numbers intact to show you that I stole it off the internet. All right, and it's on the worksheet. Look at your calendar. Well, obviously you'd have to be at the calendar if you were watching this video. But anyway, I like this worksheet because it makes you use many rules of exponents here, like 6 times 6. What are you supposed to do with these exponents? Oh, and by the way, the answers are right here just so you can check yourself before you wreck yourself. All right? So use a power of exponents rule, or adding exponents rule, numbers of the same base. And then remember what I said yesterday. You have to get this to be the same base. All right, and then like I said yesterday, the reason is that funky math. It's not funky. It's actually very simple. It's matching math. This happens all the time. What does x have to equal? You don't even have to know what log even means. You're not doing a logarithm equation. You're doing matching. So 6 to this power equals 6 to that. The only way that's true is if this equals that. If this equals that math, I don't know what else to tell you. Why I like this one so much is you have to, you can't just add these exponents. These have to be the same base. And 243, I don't think that's 9 to a power. Let's see, 9 times 9 is 81. This is old school math. Oh, I already know that this is because it ends in a 9. So, well, actually what you need to do is get that to be 3 to some power. All right, and then, I don't know, it's so early in the morning. I haven't had my coffee yet. Crabby. But let's just analyze it with the calculator. Why I'm doing this online, I have no idea. I knew it! Okay, so it's 3 to the 5th raised to the k plus 2. And then times, well, this is 3 squared raised to the 2k minus 1. And this equals, well, what the heck? 3 squared. Can't do any comparisons yet, but this times this, 3 to this power times 3 to that power, you add these exponents. But you better distribute, because this is a power raised to a power rule. So we need to distribute those exponent values there. So this is 5k plus 2k, which is 3 to the 7k. This is 10 minus 2, which is 8. And then that's what 3 squared equals. Then 3 to this power equals 3 to that power, only if this power equals that power. Subtract 8. I feel like I did something wrong. 5 times 2, or 5k, 4k. I never was good at math. 9k. There we go. All right, because I saw that answer. So I made a boo-boo. 9k, subtract, then divide, and then that's how we reduce and get negative 2/3. Whew. Should stop and get my coffee. All right, same old, same old. I think I don't have to do this one, but this one we could compare to 4 because this is 4 cubed, or you could do 2. This is 2 to the 6th, whatever. This is 4 to the 2r times 4 to the 3rd raised to the 3 minus 3r. And then you go from there, almost exactly like the last question. Distribute, add these exponents, and then compare the exponents. Okay, so on your worksheet, there's a few of those. There's a division question. Just use your division rules. And then I added this. I took these directions out of the book. Really, domain and range are nice. All exponentials are continuous. I mean, let's just figure that out. It's either increasing or decreasing. So say it's increasing or decreasing from negative infinity to infinity. You'll see that. There is no symmetry, so don't worry about it. It will be bounded or above or below. All right, so pay attention to the asymptotes. There are no extrema, and there definitely is an asymptote, and then the limits. So I want you to answer that on the worksheet graphs that I applied for you. So you're at 0, 1. All right, and I love this, analyzing that coordinate for the parent graph. And then negative 1, 2, and 1, a half. All right, I'm going to pause the video. The Rugrats are up. I'm going to go check out them. Okay, so again, I'm kind of graphing this back from the Rugrats. They're getting breakfast right now. Probably hear them scrummaging for food like rats in New York City. By the way, did you see that rat pulling the pizza down the stairs? Amazing. Look that up on YouTube or whatever. But okay, so after you're done graphing in the worksheets, and again, I put this on the calendar. You can just put the worksheet questions on your homework. Don't worry about printing the sheet out. It should be fine. You don't get a glorious grid like this, so can copy it on your paper and save trees or whatever. But anyway, we're going to answer all these questions after we're done. So this is the parent, all right? And then what happens is it gets stretched vertically by a factor of 4. But let's just analyze this. What happens is 0, 1 becomes 0, 4. Because I plug it, this is for the parent now. 0 plugged in for 1/2 raised to the x becomes 1, but then you take that y value and multiply it by 4. Then it gets moved right 1, and you could do either or. These are independent of each other. They don't affect each other. Move right, then multiply by 4. Then go down 2, all right? And then that's where this new point comes in. But keep in mind, down 2 also affects the asymptote. And I should change colors on that for what the new point, because this is actually a point on my graph because I did all 3 things to it. All right, and then -1, 2 goes right 1, and then 4 times 2 is 8. So there's a little bit steeper. You can see that, the stretching vertically compared to that. Oh, I'm sorry. I didn't go down 2 though, but still stretch vertically. So let's do that all over again. Right 1, 4 times 2 is 8, then down 2. My bad, dogs. And then I'm tired. 4 times 1/2 would end up being, well, let's do it. Okay. So there goes the TV. I have to concentrate here. SpongeBob in the background. What the heck is this? 1/2? All right. So 4 times 1/2 is 2. Then right 1, and then down 2. Okay, so let's make sure I did that again right. 1, 1/2. 4 times 1/2 is 2, and then right 1, down 2. All right, you're still going to get to this asymptote. It's going to take a little bit of a while, though. So there's the picture. Okay, and then because of time, domain is all reals. Try to go real fast on this. Range is affected by that asymptote, which is -2 to infinity. Increasing, it's increasing, or this one's decreasing from -infinity to infinity. DEC as opposed to domain. Finger going down as I read left to right. Boundedness, it's bounded below. Bounded below. There's a boundary below it. Very simple. Asymptote is y equals -2. And I don't have time for this, but the limit as x goes to infinity is -2. The limit as x goes to -infinity is positive infinity. And you write it. Do as I say, not as I do. Okay, now, blah, blah, blah. Okay, did that one. So now these goofy little things. You can see what I have left. Okay, in addition, in your homework, back to the book, we're going to go to the logistic function. Okay, this is in your book. This should look familiar. If you want to get your book out for memories, go right ahead. Remember, when I talked about the logistic function, it's more like what real-world population actually does. There's a limit at some point. So exponential growth would take off and just spike forever. All right, well, that really can't happen unless we leave the planet, because planet Earth will limit our growth as it is, because we have limited, space. So until we go to Mars or some other galaxy, but I can't wait, Earth is going to limit and stunt that growth. So that's, what happens, it levels off. I use the bacteria culture in a Petri dish as an example of, that bacteria having limits of how fast or how much it can grow. So anyway, you're not going to have this memorized per se, but the first question, which I just stole, example 8, it's actually a calculator conundrum, especially those with the cheap TI-83s, which is fine. I'm not ripping on your calculator. I love the 83. But with the 83, you don't have an option for a fraction button. So when they say, here's the model for Dallas's growth, this just means Dallas has, some limitations. Dallas is only like this big, so the population can only fill up so much in this little space that it has. And then what happens is if we run out of space, people start leaving. Well, that means this little area has some limitations about how much it can grow. So that's why we're exponential, and then, well, Dallas is only so big. Okay, so hopefully you get that. But anyway, it's a calculator question. When will it reach 1,000,000? Well, that means this is 1,000,000. That means I have to solve this, equation, which means we can go to the graphing calculator and do y1. Ugh. Okay, this is what I mean about those 83s and 83 pluses. Without a fraction button, you need parentheses for the denominator. And I put them in black. What's the most important? Because when you do e caret for this, 21 blah times e caret, these are forced upon you. All right, so I need those for the e caret, but then I need these for the denominator. Biggest mistake students make. That's why I'm, doing this and taking so long on this. All right, and then you put y2 equals 1,000,000 and find the intersection of these two. Well, first of all, your window, well, look at what happens. It happens in year 84. So guess and check. Hey, this may happen 100 years later. Why do I know that? Because it starts year 0 at 1900. And actually I have a question. What is the initial population in 1900? That comes from plugging in 0 for t. That turns this into 0. Careful on this. E to the 0 is 1, but then 1 times 21 blah plus 1, that turns this down to 22 point. So the initial population, easy for me to say, is 1.3 million divided by that 22.602, and then you get that answer. So anyway, my point being, you need to have some sort of idea that this may happen 100, 120 years later, so your X window should be 0 to 100. And then, you're killing me if you don't understand your Y window, because you're checking for Y equals 1,000,000. So I always like to go bigger on that. All right, so I do 1,200,000 just to see that horizontal line in all its glory. Okay, all right, so moving on. This one is right out of the book, and it's logistic. So it says, use a grapher to graph the function. Find the y-intercept. Bull honkies. You can find the y-intercept right now. You find a y-intercept by plugging in 0 for x. I don't even want to put a negative in there. Like I said, I'm tired. What's e to the 0? 1. Good answer. No time. 2 times 1 is 2. 2 plus 1 is 3. The y-intercept's 3. We better see that on the graphing calculator. Let's go to that grapher. I'm not even doing the Inspire. No time. Thing works all jacked up on my calculator. Computer! 9 divided by, we're going old school. I'm doing an 83 plus. So just as long as I have parentheses for the denominator started off right there, I'm good to go. E is in 2 spots, here or here. I use the E to the X button, so I have my exponent thingamajigger done. Well, actually, with this fancy schmancy, I don't even need extra parentheses. For an 83 plus and an unupgraded 84, you'd have a parenthesis, negative x, close parenthesis, and then another parenthesis for the denominator. Okay, zoom standard 6, and then hopefully we see something we may have to zoom out. Now, how do I know where that asymptote is? I can see that asymptotic behavior, and there's y equals 3 for the, well, I'll get marked wrong so quick, my head will be spinning, 0, 3 for a y-intercept. And then as I plug in big negatives, which is a bad way of saying it, you can see that there's some asymptotic behavior, that those values are getting closer to 0. And then when we get big for the y values, the x values, what does it appear that we're approaching here? Well, I think we can see it in the equation as well. Is that really 9? No, it isn't, because these are decimals that are just so far out. It's like 8.99999999999. You get it. So the graph of this goes through 0, 3, 1, 2, 3, and then has a 4, 5, 6, 7, 8, 9 horizontal asymptote at 9. All right, and then it does this, and then goes through like that. So there's a sketch of it. Your horizontal asymptotes are y equals 0, y equals 9. Hey! See that? Okay, great. Alright, same thing. Hey, last 2 examples. Let's just double check. Yay! Alright, So use a grapher to analyze this. Okay, remember I told you e to the x, when we're looking at it, just graph 2 to the x. Well, no more. E is 2.718. Okay, so when we look at the parent graph, it's 0, 1, and then 1, 2.718. Ain't no thing. And then negative 1, 1 over 2.718. There's the parent. I'm not graphing it all the way through. What I'm going to do is the things that happen with the graph here, you know, as far as the vertical stretching, and I'll check it on my calculator. This is going to be crazy. First things first, this 4 is a vertical stretch. And then we have a horizontal shrink, which, again, this is rewritten, I can write it right here, 4 times e to the x over 1/3. Then we'll check Samuelis's you know, mathematical abilities on this. So 4 is a vertical stretch, so 0, 1 becomes 0, 4, and then it gets horizontally shrunk by a factor of 1/3, which means the x value gets multiplied by 1/3. That's what's mind-blowing. But that doesn't change this coordinate. Okay, that you know, the x coordinate's already 0 for this. This one's actually a little interesting. This is 1, 2.718. I take that 2.718 and I multiply it by 4. That's like, I don't know, close to 11. I can't even count. I don't know, somewhere around there. Just take 4 times 2.718. Do it yourself. But then this is 1 comma. Now it's a 3rd comma. So there's the horizontal shrink. All right. So this sucker really gets bent up and all mishmashed and everything. All right. So then this one, 4 times 1 over 2.78 is approximately like 2. You know, because 4 over, actually a little less than 2. So this negative 1 comma 1 over 2.718, 4 times that, you're somewhere over there. And then it's 1/3 of that. Holy crap. So this graph gets really what looks like steep by these two changes. But you know what doesn't change? Asymptote. Okay? So that would be the picture of that. You can look at this on the graphing calculator. I'm curious. Let's go ahead and do that. We got the time. I got 6 minutes before I got to leave. 4 times e, all these things I do for you guys, e 3x. We can expect something. I could probably barely see this on the graphing calculator, how steep this sucker is going to be. There it is. Okay, and just like I said, 0, 4, you can see that, and then it's real tight there, but then it still goes bloop. All right, and then the last one, you know, this is the same as this, and I'm not even going to go through it because of time here. So use a grapher to find out y-intercept and the horizontal asymptotes. You know, do that for this. You're going to get something very similar to this graph, but then you can answer these questions. You know, like let's look at this picture up here. This one's, the domain is all real numbers, but the range for this one is from 0 to 9, not including 0 or 9. It's continuous forever. It's increasing forever. There is no symmetry. It's bounded, which means bounded above and below. There are no extrema. There are 2 asymptotes for this one, y equals 0, y equals 9. And the end behavior, oh, this is interesting. As x goes to infinity, y goes to 9. As x goes to negative infinity, y goes to 0. So you could do that with this one because it's a logistic function and, you know, something similar. I wonder if that's going to be one of the asymptotes. Who knows? All right. And then I wonder what the y-intercept is going to be. E to 0, 1 plus 2 is 6 over 3. Anyway. So you can do that, and I think you're fine. Have fun today. I'll miss you.